All right. I have been asked if you can do that one using that bent wire method or Mueller-Bress law. Yes, you can. But when these things turn out to be more trouble than they're worth, then it's just not worth it. Just go ahead and put the unit load on the thing and solve for the force in the member. It is helpful even if you don't have values. For example, let's say you've been asked for the influence line for the force D, E, F, G, H, I, and member BI. And member BI is what we're looking for the force. Then I would shorten BI. In other words, I would like tension it up. And that would make a panel of some kind by shortening this diagonal length. If you were to make 4 bars and put links on the bars, just that panel, serrata, what would you get? Have no idea. But got a really good telephone number, didn't you? Yeah. What happens is when this bar right here gets shorter, it simply pulls this bar up to here. And you say, well, I don't think it pulls it up to there. I think it arcs it back to there. Well, there's no difference in what you said and what I said. You just pulled yours up too far. You should have just pulled yours up only a tiny bit. So when you pull this point shorter on that diagonal, this bar arcs. Yes, if you go 18 feet, it arcs to the left also. But just up a little, it goes up to there. This bar moves to here. Since this bar here is unaffected, he didn't even know what you're doing. The bottom of the bar goes to here, so the top of the bar goes to here. And then this bar goes there, and this bar goes here. And that's what that panel looks like when you made this diagonal 1/100 of an inch shorter. So I'm going to draw you that panel. That panel goes up to here. That panel goes up to here. And that member goes like this. And then, of course, the new diagonal that's a little bit shorter does go over to there. You'll notice that member CI was vertical before we started. And even if you want to try and make me roll it slightly back, both of them roll slightly back, so member CI is still vertical. That means that everything hanging off of CI is horizontal. And it looks like that. And so I guaranteed you that that was the influence line. And I never guaranteed you that you had it situated properly, but I guarantee you what you see there, A, B, C prime, D prime, E prime, F prime, G prime, that's the influence line. It is. And so you say, well, all right, you're saying that this is the influence line. I say, yes, it is. And you say, well, all right, so you're telling me the influence line has a 1 if I put a unit load at F. No, because it's your problem to make the thing fit back where it used to fit. It's your job to bring that back down to here. Now, I'll admit to you that the problem with this method is when you take a 1, and you got to take a 1 out. When you take a 1 out of that member length, that does not raise this point up by 1. It moves it up higher than 1 because you took the 1 out of the diagonal. For example, if you had a panel that looked like this, and you took a 1 out of this member, that sucker would raise way up in there because this member here getting a little bit shorter raises this up a lot. Actually, it's a determined amount. What this number right here, this raise up is, if this length right here is 15, and the length of this member was originally 10 squared plus 15 squared, take a square root. You got a calculator? Got a calculator? Got a calculator? Got a calculator? Somebody gonna, how much? 18.03. 02, thank you. I could care less, either number's fine with me. Then it turns out if you take a 1 out of here, you will actually raise this value up 1 times 1802 over 15. You're moving it up along the 15 slope, and you're shortening the diagonal by 1 along the 18.02 line. It raises up higher than the number. I don't care if you remember that. I don't even know if you ought to remember it. I don't even know why I remember it. There's things I've forgotten that I wish I remembered more important than that. But, it does give you this number right here. This guy right here would be 18.02 divided by 15. But I will tell you it's kind of valuable just to be able to do that, because now that I can tell you what the influence line looks like as I bring this point back down to where he ought to be. First off, it's rotating the whole mess about point H, and I'm rolling it down, and therefore this end will go up to probably about here, and then that one will go back through the 0 point. And since you're rotating this whole thing this way, that means this one actually is going to kick up. And so here is your influence line. You say, well, great, I can do that. I still don't have any numbers on it. But I'll tell you what, I have seen your work. I've seen what you handed in or what you brought by my office. You said since you couldn't do this, you were going to put a 1 here and solve for the force in that member, and you did. Very, very well, I might add. You cut through the member, you drew a free body, you found the reactions, you sum forces vertical, great job. Then you put the 1 here and you drew a free body. Then you drew the 1 here and did a free body. You did the 1 here and did a free body. And you did a 1 and you did a 1 and you did a 1, and I looked and you had 19 free bodies on the page. So why you got so many free bodies? I don't have any idea what it looked like. So I had to do them all to make sure I got the right answer. At least with this, I can tell you what the answer is. You put the 1 there and give me that number. And you put the 1 here and you give me that number, and I guarantee you can go home. And just a couple of things on there, since I know what the influence line looks like, I don't know its values, then I can tell you only need 2 free bodies, 1 with a unit load here and 1 with a unit load here. And from then on, it's guaranteed it goes down to 0 at this point, and then it goes negative. So it's up to you, whether you use it or not to save some time. That really is probably more for beams. It works better for beams than anything. It works for this, but not very well. Forget it. I have no idea what that thing looks like for the influence line for this member right here. I know it does something, it gets short, and that rolls this thing up, and then this thing here, I don't know. I would just go sticking 1 pound loads all over the place and get the influence line. All right. Now, you will find, thank you, you will find that when you have statically indeterminate structures, then you know that was a pretty good structure for you. Tinkered with it, incidentally. It was statically determinate, and I could design it. I mean, I'm sure it would be very expensive, and it would be very deep. And then when you decided you couldn't pay for it because you couldn't hardly get across 160 feet with anything of a reasonable size, you decided to put another support under it, and you decided to put another support over it when this load goes on down here. 50 feet and 50 feet. You will have to complement your statics equation with some compatibility equations. You will have to come into this beam with the original loads on it. You'll have to say it deflects like this, which is unacceptable. There will be a deflection at this point, which is not what you want. And there is a deflection at this point, undesirable. And then you will come back in and you'll put a force on the structure at this point where you don't want any deflection, and you will get some deflection at both of these points. You might call this one delta 1, delta 2, big delta due to the real loads. Once you put a force R2, let's call this one R1, R2, R3, R4. Once you put R2 on the structure, it will cause some deflections. Call it maybe the deflection at location number 1. We call this one delta 1. Say delta number 1 times how much force you put on there. And while you're trying to get rid of this delta 1, you'll also be getting rid of a little bit of this deflection over here. And so that would be the deflection at spot number 2 times R2. And then you'll try your best, but you'll find out that these two won't go away just under the action of this single load. In other words, if you make this go away, that one won't go away, or it'll be too big.
That won't be delta 2.
You know what we ought to do? It shouldn't call, let me just not give these names. And then call this the deflection at point 2 and the deflection at point 3. You got your choice of names. And then this would be the deflection. Here, let me give it a more complete name than that even. This is the deflection at point 2 times, for right now I think that's good enough. The deflection at 2 times reaction at 2. And this is the deflection at 3 that you got due to a unit load because you put a load at point number 2. Let me just say now, I don't care what you name it, because the naming is going to be different as soon as we start learning how to do this anyway. What an optimist. What an optimist. I've never seen such an optimist. Well, you've been here 5 minutes and you're checking your watch. What an optimist. Yeah, it's not time. It's not time. Then so you will come in, I don't care what you name it, probably those are bad names. And hey, oh, thank you, R3, and you'll find that it causes some deflections like this. What you'll have to do is you'll have to very finely tune R2 and R3, such that when you get through, these two will add up to that, and these two will add up to that. Now, the only reason I'm telling you this in the first place is you're going to have to be able to solve for deflections to get these equations to complement your statics equations. Maybe I didn't even mention it. Maybe I just think you know it by now. If you have two reactions on the ends and you have no horizontal forces, you have enough equations to get the job done. But when you add a support, it's all over. Your statics just doesn't have the ability to solve for these extra unknowns. So that's why we're going into deflections. I know you like derivations, so I thought I'd pull one out of the hat here. I got a member subjected to bending. I'm going to put a moment on each end of the member, and it is going to cause the member to deform. The original length of the member is that long. We'll make it short enough so that the moment on each end can be reasonably considered to be the same. In other words, there's not enough distance across the bottom to say that this is M and this is a change in M. And it's going to form an arc, which is going to, if you draw a straight line, cross at a point above the beam. I'm going to call how far it is from that point to the centroid, to the neutral axis of the beam, or the neutral surface of the beam. Arbitrarily give it a name rho. The beam has some depth to it. I'm going to tell you that someplace there's an outside fiber. We commonly call it C for our equation MC over I. And I'm going to show you that the beam that used to be nice and rectangular looking is now deformed. First off, I'm going to tell you that the beam has rolled to the right on the left end and to the left on the right end, d theta 1, d theta 2. I'm going to come up here and measure between parallel lines, show you that interior angle is d theta 1, d theta 1, interior angle d theta 2, d theta 2, d theta is equal to d theta 1 plus d theta 2. Widen this thing out, doesn't need to be that close anyway. All right. Now then, d theta is, this little angle right here, d theta 1, is opposite over adjacent. dl1, the lengthening of this fiber, divided by how far it rolled around that neutral surface. That's d theta 1. D theta 2 is on the other end. And I'm going to tell you that dx got a little longer by the amount dl1 and dl2. dl1 plus dl2 divided by c is just total dl, change in length of the whole bottom fiber, divided by c. But you know an equation for a change in length. A change in length in something is strain times its original length. So I can substitute back in and tell you that d theta is equal to strain times dx is dl divided by c. Dividing both sides by dx, I'll tell you that d theta dx is equal to the strain on the bottom fiber divided by c. Now, if you say, I don't know where we're going, I'm not sure this guy knows where he's going. But all I can guarantee you is you will end up here. From 305, you did have 305. Strain in the x direction is related to stress in the x direction by E. There's your stress-strain diagram. E is the slope. Here is your sigma x. Here is your strain. And the slope of that is E. And you also derive the equation that stress is equal to MC over I for bending in a beam. So that strain in the X is equal to sigma X MC over I divided by E. D theta dx, you told me, was strain over C. D theta dx is strain divided by C. C cancels C, so d theta dx is m over EI. Now then, S equals R theta. Anytime you have something that rolls through an angle theta, that arc length, at a radius r, S equals R theta, then I'm going to tell you that dx is equal to rho d theta. Let me see over here if I believe that. Here I start here, and you know these are very small. They're only shown like this so you can see them. And I'm going to tell you that dx is equal to rho, the radius of curvature, not this one, but this one, rho times d theta. That tells me dx. You say, well, not really, that's the arc length. For how high this point really is above the floor you're sitting on right now, you're talking about a tiny, tiny angle. And therefore, I can tell you that the arc length of that is the same as the original length dx. So dx is equal to rho d theta. And therefore, d theta over dx is equal to 1 over rho. Goes on the other side. But you just told me d theta dx is m over EI. And therefore, 1 over rho is equal to m over EI. That's what they call the curvature. And that tells you, it gives you an actual number for this radius of curvature, depending on your moment and your modulus of elasticity and your moment of inertia of your beam. If you got a very big beam with a great big eye, it won't have much curvature to it. The more moment you put on it, the more curvature you'll have. Now, I wonder if I brought that. Been a while since I've seen that. Probably been a while since you've seen that. I don't think I brought that with me. But I went out on the internet. What a wonderful thing. And I stuck in 1 plus pren dy dx pren raised to the 2, and lo and behold, a half a dozen mathematicians proved to me that 1 over rho in the calculus is d squared y dx squared divided by 1 plus dy dx. Let's see. It's not impossible I got it in this mess somewhere. No, I don't think so. I'll post it with the notes just so you'll see it and believe it. Now then, we've got an equation for 1 over rho, and if you'll let me say that the slope of the beams that we are interested in are small, and if you'll look at the floor you're on right now, you'll notice that the slopes are pretty small. A degree, probably not a degree. And then you square that in radians. This term here is goes to 0. 1 of the 3 halves goes to 1. And you can say that 1 over rho is pretty close, this right here. Now, that's not true for the people who work offshore and hang this pipe down 6,000 feet to the ocean floor. They can't throw this term away. But generally speaking, you and I get away with that. That says that 1 over rho is equal to d squared y dx squared. And 1 over rho is equal to, forgot what it was equal to. 1 over rho is m over ei. And therefore, 1 over rho is equal to d squared y dx squared is equal to m over ei. Look what that did. It relates the vertical motion of the beam to the properties of the beam and the moments that you apply. In other words, it says, did your beam deflect y? Yes. Can you take the derivative of the equation of that curve? You say, well, if you'll give me the equation, I guess I could. I say, then can you take another dx of it? You say, I could probably take 20 of them. What's the point? But once you take 2 of them, you have somebody else that you know. That's the bending moment in your beam. So if you can get the equation for the bending moment in your beam and integrate it a couple of times, I'll tell you where the beam went, how far up and down it went. Now that's good for some beams. It's good for all beams. It's not hard to do for some beams. Some of them get pretty messy. And so there are other ways that you can solve for deflections. But I'd like to mention that this particular method has a particular nifty point. It's continuous. You want to know the deflection at 1 foot, 2 foot, 8 foot, 6.333 feet. This guy gives you the answer because it's a continuous equation. First you'll get the slope, and next you'll get the deflection. All of the other methods, in general, they give you the answer at a point. So if all you need is where did this thing go at 6 feet, then there are other methods that probably beat this method for getting you an answer in a hurry. Now back to the case you and I had. That really looks like, since you only are interested in deflections here under various and sundry loadings, then I would say probably this double integration method wouldn't be your first choice. If on the exam they say solve for the deflection as a continuous function of x from the left end to the right end, then you're stuck. You gotta do it. Here's some of the methods. Double integration. There's a thing called moment area, elastic load, conjugate beam. There are work energy methods, generally virtual work. There's a couple of sub-methods. We'll cover this one because it works really nice, and it always works, and it's nifty, and it's easy. And we'll cover this one. This one is location specific, and this method gives you answers as a continuous function. Then there's, we cover slope deflection in here, so there'll be a little bit of slope deflection too. All of them require that you be able to write moment equations and draw shear moment diagrams. That's critical. A quick summary of your supports. Pins cause the following boundary conditions: no deflection, rotation. If you want some, that's okay. This one, of course, you would say no deflection, and rotation is okay. This one would say no deflection. Deflection this way is unknown and can happen, and rotation is okay. This one says no deflection in that direction. Movement and rotation acceptable. For a fixed support, actually, this is a pin, and here's your rollers. For a fix, I'll tell you y is equal to 0, x is equal to 0, and the slope is equal to 0. Because once you start working with these equations and start integrating them a couple of times, you're going to find that you keep getting these doggone constants of integration that pop up, and this is how you will evaluate them. All right, let's try one. I've got a beam. Simply supported on each end. Triangular load. 2 kips per foot. Spread over 12 feet. I'll tell you that the beam has a moment of inertia, and it's made out of a material. And I can tell you what EI is if you want. And if EI is given in inches to the fourth and pounds per square inch, then I can change them to these units. Or if you'd rather, we could go ahead and change these units to inches, kips per inch and inches. Take your choice. But for right now, I'm just going to say it's EI. Controlling equation. D squared y dx squared is equal to m over EI. Engineering equations are really nifty. First, you figure out what kind of a problem you have. I got a torsion problem. You go find the equation for torsion stress. It says Tc over J. From then on, it's all easy, because you need torque, you need the radius of the shaft, and you need the polar moment of inertia of the shaft. He tells you what you need. Here's a controlling equation for deflections on a beam. You need to know the moment, and you need to know E, and you need to know I, and I'm going to tell you I'll give you that. In fact, I'll just probably go ahead and use these units here, and I'll change this E to kips per square foot, with a couple of 12s usually, and I'll change this into feet to the fourth. First, I got to have the moment. The reactions. If you don't mind, I'm going to lie about this load. I'm going to concentrate it at its centroid. I'm going to replace the distributed load with an equivalent concentrated load. The amount of sand under a thing like this, that's base times height over 2. Base is 12, height is 2, cut in half, 12 kips of load. Location of the centroid, 1/3 of the distance from the fat end of the triangle, 4 feet, 8 feet. Got a calculator? Oh, look at that, ready to go. 12 times 4, never mind, sorry, I just noticed, divided by 12. 12 times 4 divided by 12, 4 kips of reaction. Some moments about this point, 12 times 8 divided by 12, 8 kips. Some forces vertical, looks good. Here's my moment. How I find the moment is I come in here and I cut through the beam at X. X can be measured from either end. X can be measured from down here somewhere if you find it would be more convenient for you. Well, that's pretty much up to you. I'm going to measure X from the left end. Here is the piece of the beam. Here's where I cut it. Here's this left-hand reaction, 4 kips. Here is the dimension, X. There's a shear at X, and there's a bending moment at X. You will notice I will always put the bending moment in the positive direction, no matter which way it really goes in that beam. For example, if you ever see me with a piece of steel like this, and someone has a load down like that, and you have seen me cut the beam, you know which way that moment's going to go, and you know that's wrong. But I'm going to always put that moment in the positive direction, such that it causes compression in the top and tension on the bottom. That way, if the moment equation wants to come out minus, that's his problem. And I'll throw the minuses into the equations that we've got here. Then on top of the beam is a thing that looks like this. I'm going to tell you that this is, let's just say Y worth of load, Y tall. You'll notice it is not 2 kips per foot, something less. And therefore, I'm going to again replace this load with an equivalent concentrated load at the centroid. Here's the beam that we're going to be working with. There's the moment at any point X. Here is the 4-kip reaction. Here is the load that we have cut off as we moved X. Let's see how much load we have here. Y is this number right here. Y is to X as 2 is to 12. Y is to X as 2 is to 12. I can tell you how high the sand is stacked at X. Y is equal to X over 6. Check it out. When X is 0, Y is 0. Good enough. When X is 12 feet, 12 over 6 is 2. Good enough. If you ever write an equation down and you can check the end values, it probably makes sense, just to make sure your equation's probably right. Gee, nobody's sleeping yet. Maybe he is. Roberts? 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 Is he dead? Roberts? There we go. Good morning. Boy, your eyes are red. Oh, my goodness. Roberts, if you have a triangle whose base is X and whose height is X over 6, how much sand is underneath the triangle? Hint, hint. A little too soon to ask questions? It's just the area. Just the area under the triangle. What's the area under a triangle? I didn't really hear that. Did you say BH over 2? Very good. You lie. It is the base times the height divided by 2. And the base is x, and the height is x over 6, and it's divided by 2 because it's a triangle. And therefore this load right there is x squared over 6. This dimension is x. This dimension is x over 3 to the centroid of the triangle. And therefore we ought to be able to sum moments about the cut face and solve for the moment. If it comes out a negative some of the time and a positive some of the time, that ought to be taken care of inside the equation. Sum of the moments about the cut face is equal to 0 is equal to minus 4 times his moment arm. That's because he's rotating not the way my right hand is made, plus x squared over 12 times his moment arm, x over 3. That's a positive because that's the way my right hand is made, plus m sub x. And therefore the moment at any point x from 0 to 12 can't go to the left of this point, can't go to the right of that point. It'll only be good for that region. Is equal to 4x minus x cubed over 36. All right. And you've told me that, let me move the EI over on this side so it doesn't really get in the way. You have told me that EI times d squared y dx squared is equal to m, which is 4x minus x cubed over 36. I ought to be able to integrate that once and get dy dx. dy dx is the slope of the beam.
Is it also the shear or derivative of the shear?
No, now it won't give you the shear now. See, you're going the wrong direction.
So derivative of moment shear.
You'd have to go a d cubed y dx squared to get back to the shear, and you'd have to take a d fourth dx to get all the way back to the load. So actually what we've done is we could have written an equation for the load actually, and then integrated it once to get d cubed y dx squared, that'd be shear, dx cubed, then integrated it, and we would come up with this equation. What we do is we just go ahead and write the moment equation directly from a free body because it's a lot easier than doing the previous two integrals that you'd need. But the integral of the load, it is the shear. And the integral of shear turns into the integral, turns into the moment. And then this EI kicks in at this level, so up to there you didn't have any EIs. Now then all of a sudden it turns out that the moment does curve the beam, but it is influenced by EI, so that has to drop in at this level. All right. EI times dy dx is equal to, Crawford, keep you awake here. Well, but this is it. This is whatever comes after. It's the right answer, but you know, I'm not going to let you get off the hook that easy. Integrate that term for me. Good. Yeah. Uh-huh. Oh. Okay, you integrate that term one time, minus x to the fourth over 4. Let's just don't bother with the numbers. Just say 4 times 36. And then you pick up, sadly, a constant. That's correct. Call it C1. And you have EI times y is equal to 4x cubed over 2 times 3 is 6 minus x to the 5th over 4 times 5 times 36 plus C1x plus C2. Okay? Now we're in good shape. We have good equations. The only problem is we don't know the magnitude of these C1s and C2s. We get them by telling these equations that are general and don't know how the beam is situated, doesn't know if it's fixed on the left, or free on the right, fixed on both ends, he just doesn't have any idea. You tell him that he must meet certain slope conditions. He must meet certain slope conditions. Well, you know what? Well, just notice that. We don't know any slopes. I guess he can do whatever he wants to on the slope equation. We do know deflections. What do we know?
Deflection at E support is 0.
At x equals 0, the deflection is 0. And at x equals to 12. Those are called boundary conditions. Believe me, if this had started out living as a cantilever beam, and of course the moment equations would have been different too, then the cantilever beam would have a known slope and a known deflection at the wall. So all we got to do now, go back in and tell him about these things. Hey, equations. Yes, master. EIY at x equals 0 is equal to 0. And so we simply go in here and we say 0 is equal to 4 times 0 cubed over 6 minus 0 to the 5th divided by 4 times 5 times 36 plus C1 times 0 plus C2. And lo and behold, we've evaluated one of the constants. Next, and now really, probably best to say boundary condition number 1 at, you don't have to if you don't want to, at x equals 0, comma, y is equal to 0, but sometimes you really need them all written down so that you're careful when you plug them in. Here's boundary condition number 2. At x equals 12, y is equal to 0. So 0 is equal to 4 times 12 cubed over 6 minus 12 raised to the 5th power divided by 4 times 5 times 36 plus C1 times 12, and then there is no C2, is equal to 0. And that lets you solve for C2. And if you've got a number for me, I'll certainly take it, but I have very little interest in it. I know I'm good to go. When the prof asks me for the deflection at the middle, I'll simply take the number I got for C1 and plug it in right here and go at x equals 6, x equals 6, x equals 6, and I'll crunch out a number for him. If he asks me to solve for the maximum deflection, the maximum deflection occurs right about here. Looks like it's probably not at the center. See how the maximum deflection is a point of 0 slope? And then I would go to my slope equation right here, and I'd plug in, I'd leave x as an unknown, and I would set that equal to 0, and I would go get EES, or Maple, or what else do y'all use for MATLAB? Any of those things, because I sure wouldn't do that by hand. I'd plug in 4 times x squared over 2 minus this times that plus C1 is equal to 0, and I'd hit a button. A lot of you, I think your calculators even do that, don't they? Yeah, so not much to it. And if you don't have a calculator that does that, don't buy one for this class, because I'm not going to ask you a question like that on an exam. But I know you have access to EES. If you don't know how to use Maple or one of those other things, then I highly recommend EES. It's totally transparent. And you just turn it on, you literally just type in 4, you put in a times mark, X, you've raised to the 2 power divided by 2 minus so-and-so, and you hit a button and it gives you the answer. It's really nice. All right. Let's try one that looks maybe a little simpler than that. You better hurry back. You're going to miss the dancing bear. Here's the beam. Here's the load. That's 30 kips. That's at 5 feet, 10 feet. I'll leave it for you to check the reactions. And we're going to say that d squared y dx squared is equal to m over ei. Now, we do have a little problem here because the moment is not a continuous function from end to end. And so we're going to have 2 moment equations, and then we're going to have to tie all this stuff together. I will go ahead and show you the deflected shape. Maximum deflection doesn't occur in the middle, and it does not occur under the load. It is somewhere between those 2 points. Let's call this region 1, and let's call this region 2. To get the bending moment equation in region 1, I will do the same thing I always do. I cut the beam at a distance x. I draw a short little piece of member with a 20 kip load on it at a distance x. I put a positive shear on it. You know, a lot of times you won't see that shear. I'm not sure if the book even bothers showing it. Since we're going to sum moments about the cut face, since the shear does not come up in this equation, it influences it because it changes the moment equation because it's obviously it's 20. But you may not see that in the problems in the book. Here is m, let's call it m sub 1. It's in region 1. This equation will be good from 0 to 5, and that'll be it. Johnson. That's not Johnson. Love. Love. You ought to at least get up when your name is called. I mean, you know. Give me how big moment 1 is. And I mean, I know I had a prof boring like this too. I mean, it was just agony. But 20x, go back to sleep. Well, I've always told you can do this in your sleep. You never believed me, but 20 times x. And if you're uncomfortable with that, then for heaven's sakes, sum of the moments about the cut face is equal to 0 is equal to minus 20 times x plus m in region 1, and therefore m in region 1 is equal to 20x. Now here's a free body for region 2. I think I'll just go ahead and keep x the same. That way, when I try and tie these together, x is equal to x. You don't have to. You could draw your moment equation coming from this end with x coming that way. And later on, when you tie these two regions together, when that x was a 5, this guy would think his x is a 10. But it's your choice. 20 kips, 30 kips, 5 feet, cut face, positive shear, positive, you better remember to put that moment in there in a positive direction, because you'll get some weird results otherwise. Sum of the moments about the cut face is equal to minus 20 times x plus 30 times x minus 5 is his moment arm, x minus 5, plus m2, which of course is a function of x, and m2 is equal to 20x, someone wants to cut this, equals 0 equals m2 is equal to 20x minus 30x plus, there's plus on this side, minus on the other side, minus 150 on the other side, plus 150. And so that's equal to minus 10x plus 150. Now let's keep these guys separate so they don't fight. This guy here thinks that d squared y dx squared is equal to the bending moment 20x over EI. Get the EI over there just to keep it out of the way. Then he thinks that dy dx is equal to 20x squared over 2 plus C1. And he thinks y is equal to 20x cubed over 6 plus C1x plus C2. Wrong kind of 2. C2. But he only is good from 0 to 5. Outside of 5, he's a total failure. Question? Mumble, mumble? That's okay. He thinks that EI d squared y dx squared is equal to, Garza? Ooh, I caught him flat-footed. I didn't even check on him first. That's too good. That's too good. Morrison? Oh, well, now, see what we did here. Hint, hint. Turn it back over to Garza. Okay, you're just going to plug in the moment. In other words, EI d squared y dx squared is nothing but the equation for the moment that you found in this region. Minus 10x plus 150. Now, if you say, I have no idea what you're doing, but I haven't had any idea what you're doing all semester long. If you'll just, fast forward to the end of the class and let me go, I'll take your notes and I'll take the book and I'll have enough time to figure it out and I can answer your questions. That's true. I mean, it takes some absorption time, a lot of times. Now, this one I would hope I'd get a response to. This is new. I mean, you haven't seen that but for 30, 40 minutes. Yeah, seems like 2 hours. dy dx is equal to Winfield. That you should be able to do, because all we're doing is we're integrating it. That's correct. Plus 150x plus Now, I can't put C1 down here because these people are going to talk to each other where they meet. So I'm going to have to call this guy's constant a C3 because it is not this one. And then EI times Y is equal to minus 10x cubed over 3 over 2 is 6 plus 150x squared over 2 plus C3x plus C4. Now let's see what we can get without having them talk to each other. Gitman, you were pretty good on boundary conditions a while ago. But staying in this region, can you tell me anything to tell this guy?
Yeah.
Correct, you cannot. For the same reason that you got after me a minute ago trying to put in a slope, you said, we don't know any slopes.
It's curved, right? It's not straight, that line?
That's, oh, I'm sorry, what's that?
I just thought that line would be straight.
No, oh heavens, no. What a terrible thought. No, we bend beams. We don't kink them with little straight lines. You're thinking of influence lines. This is how he deflects. This is like a yardstick when you push on the middle. You know how it kind of slopes, has a changing radius of curvature throughout? All right, so the answer is no, there are no known slopes in this region, and so I cannot tell this equation, please give me C1. He hadn't got a clue. Getman, how about this equation?
Deflection is 0.
That is correct. At x equals 0 in region 1, we have a boundary condition. So the boundary condition here says at x equals 0, y is equal to 0. And therefore, 0 is equal to 20 times 0 cubed over 6 is 0 plus something times 0 is 0 plus C2. You know, this may not be as hard as I thought. So C2 is equal to 0. We don't know any more answers, so we don't know this answer here. If someone would tell me that a 30 kip load would mash this thing down 0.06 feet, well then I could stick it in as a boundary condition. If this load were in the middle, I could kind of cheat. And if the load were in the middle, I'd say due to symmetry, there is no slope in the middle of the beam. That would be acceptable because that's true. But we don't have any of those good things going for us. So let's move on to region 2. Again, region 2 has no points of known slope. We're pretty sure there's a point of 0 slope in here somewhere, but we don't know where it lives, so we don't have the x to go with it, so we can't use that for a boundary condition. But we can say that the deflection at x equals, at x equals all the way to the end, that's 15 feet, we should get no deflection out of our equation. So this says boundary condition number 2 at x equals 15 feet, y is equal to 0. We have minus 10 times 15 cubed divided by 6 plus 150 times 15 squared divided by 2 plus C3 times 15. Oh, goodness gracious. Plus C4 is equal to 0. Well, that's sad. He didn't cough up a number for us. I was kind of hoping he'd give us something. He says, I did give you something. Well, we're going to have to hold off for that. So far, we still have 2 more unknowns. Well, we have 1, 2, 3 unknowns. But we have one equation going for us that we can use later on if we can find something to put with it. We're going to need 2 more equations. Here they are. That's the answer right there. At this point right here, Mr. 1 thinks he knows the deflection, but he can't give you a value. And at this point right here, Mr. 2 also thinks it's the same number. So all I got to do is tell both of them at the same time that at this point, you guys should predict the same value. So there's your next boundary condition. At x equals 5, y is equal to, and this guy here at x equals 5, he thinks y is the same number. So I don't know what we're going to call it. Call it y prime, and call this y prime. We'll call it y sub 5. It's at the 5 foot mark. Y is equal to y sub 5. Y is equal to y sub 5. So let's go to our equations. Now we break this line and we let them talk to each other. Y sub 5 is equal to 20 times 5 cubed divided by 6 plus C1 times 5 plus C2 we already found was 0. And the other guy thinks that Y5 is equal to minus 10 times 5 cubed over 6 plus 150 times 5 squared over 2 plus C3 times 5 plus C4. And I have a second equation. What else is going on at that point? The slopes are equal. There's the slope. That's theta sub 5. Let's go talk to our theta person. Here's our theta person. Theta at the 5 foot mark is equal to 20 times, you'll have to put in x equals 5 squared over 2 plus C1 already turned out to be a 0. No, C2 turned out to be 0 plus C1. And that's equal to the other guy's opinion of theta 5, which is equal to minus 10. Yeah, I thought maybe I got the wrong equation here, but that's the slope equation. Here's the slope equation. Minus 10 times 5 squared over 2 plus 150 times 5 plus C3. I'm not happy about this, but I got EES, so I'm okay. I will literally type in, and I won't even do the calculations here. I'll say minus 10 times 15 raised to the 3 power divided by 6 plus 150 times 15 squared divided by 2 plus 15 times C3 plus C4 equals 0. And then I'll type in 20 times 5 cubed over 6 plus 5C1 is equal to 10 and 5 cubed, blah, 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 and hit the enter key. And then I'll type in that this times that squared plus C1 is equal to this plus this plus this. And I'll say, I think it's F4. I don't remember, F3, F2, F1. If worst comes to worst, you look up there and it says solve, you click on it. And he'll solve the 3 simultaneous equations for C1, C2, and C3. Along the line in the real world, I'll tell you what you do. You have this equation and this equation written down earlier also. You say y is equal to this and this and this, so that when you ask him for the deflection at 6 feet, he'll go get the C1s from over here and he'll plug them in and he'll tell you the deflection at 6 feet. And when you ask him for the maximum deflection, you'll give him, there'll be 2 equations now. So you're going to have different subscripts in the Y1 and the Y2 region when you type it in EES. But you can ask him to set this guy's slope equal to 0, and he'll come back and say, I can't do it. No solution found. And then when you tell him to try and set this slope equal to 0, he'll find the location where X will give you 0 slope. And you can take that X and plug it into Y, and you can get the maximum deflection. It's really pretty nifty. All right, I did change the problems on you. I don't remember who always was complaining because I changed the problems. If you want to work the one, I think it's 9.9. You can, but it's really ugly. So I changed it to 9.8. Take a look at it before you work the problems. Does 9.9 have 2 loads on it? Yes, it's got 3 ranges. Not good. No fun. Yes, sir.
I had a question about this.
Sure.
When you plug everything in and you put in the EI, and
Right.
then like you have to sometimes divide it by like 12, but you divide it by like 12 times. I mean 12
Right.
to like the power of whatever
Right.
the highest exponential is. Like,
Now, are
why
you
is that?
are you talking about changing feet to inches?
Yeah, exactly.
Right. See, right here we worked in feet. And so the answers will come out in feet.
Right.
And of course, theta will come out in radians. Now, the only thing is if it gives you a real beam, a real E and a real I, 9 times out of 10, E will have the units kips, which is okay, per square inch. And I will be something like perhaps 100 inches to the 4th. So you'll have the resulting units of E times I. You'll have kip inches squared. Okay? Now here's what you do. Since you're working in feet, you want to change this to feet. Okay?
Right.
So what you do is you multiply it times 12 over 1, or 1 over 12. I can never figure out which, but I know this. Inches squared have to go in the bottom, so they can cancel out inches.
Okay, yeah.
And I know there are 12 inches inside of a foot.
Right.
And I know that that won't do it because there's 2 of them. It's just that easy.
Okay.
Now then your units are kip feet squared. They'll fit nicely with the feet that you got down here. And your answers will come out in deflection in feet.
But you don't always, it's not always squared. Sometimes it's actually like 12 to the 3rd.
It depends.
Why, where do you get that?
Here's where you get this. Let's just say that y is equal to PL cubed over 3EI. And you have the length, let's say, in feet. And you want to change, you just, right now, you just want just that one. Well, this L is feet cubed.
Right. Okay. So because in the equation you have other things that are feet cubed, and you have to go and like here squared, you have to
Right.
go to whatever the highest.
Well, it's not the highest. In other words, it would be the terms in that
oh,
one.
individually.
Individually.
Okay.
See, so I'm telling you here, if you want right now to change this thing right here from feet to inches, then you would multiply it times, it's got to have feet in the denominator to get rid of this. So that's where you know what's got to go. Then that's inches per foot. Then you know where to put the 12 because there's 12 inches in a foot. And then how many of them you do to do that, you know, would be cubed. So that your feet cubed cancels your feet cubed and leaves you with inches cubed.
All right, that makes sense.
It's whatever power you're working with.
When are we going to
Yeah.
test back?
As soon as I get them graded.
Oh, they're not done
Yeah.
yet?
Well, they're not done yet. I wish they were done yet. Yeah.
Are you gonna put solutions up for them, or are we gonna go?
No. There'll be solutions up. Absolutely.
Thanks.
Sure. And they are graded just between you and me, but I got to go through them again.
Are they good or bad?
They're good. Their grades aren't high, but it wasn't the last problem, the one where I asked you to with the truss.
Yeah, the 3 forces.
Yeah, that was nothing to that. You didn't get that wrong, did you?
Yeah, I think a lot of people did.
Well, you tell me
Like,
why.
I ran out of time on it, but I mean,
Well, now that's
I
how
feel like
come.
I should have been able to do it.
Well, but you see, that's why I told you, for heaven's sakes, work 20 minutes on each problem and no
Yeah.
more. All you had to do, I don't know what this was, say 5 and 2 and 3, and I don't know what this, this length here you find. He gave you the height, I gave you the height, they gave you the base, well, it gave you the base and the base and the base.
It was just so hard to find the moment arms.
Well, then why? It's just, well, let's just say that's 2 meters and 2 meters and 2 meters and 1 meter, and I think it was 2 meters high. No.
No, it was 4 or 5 or something.
Yeah. Well, let's leave it at that for right now, because it's not going to work out what you and I got. So if this is 6 over here and 2 up there, how long is this? It's 6 squared plus 2 squared, take a square root.
Yeah.
And the spacing here is given as equal, so whatever that length is, you put one of them here, and you put one of them here, and you put one of them here, and it's 5 times L plus 5 times L plus 3 times L minus
I did
this
it wrong.
react.
I wasn't thinking.
Well, okay.
So wait, this spacing is the same as that spacing?
No. See, this is 2, 2, 2. And so that means that where these loads are is L, L, L.
Yeah.
But this is obviously 6, and that's obviously longer because it's 6 squared plus 2 squared, take a square root.
You know, I came up with something like that, but I ran out of time also. I didn't write down the final answer, but I have the final equation, so I think that's right.
All right.
What did you say you changed the problems or something?
Yeah, the homework problems, they're not assigned yet. They may be starting to be assigned today, I don't know.
Oh,
But I'm just saying, always go out, before you work the problem, go out and look at them and make sure I haven't changed them.
on the syllabus?
On the syllabus,
Oh,
online.
it's updated on the regular syllabus? That's
Yes,
all?
oh, always, yeah.
Oh, okay.
And the only reason I changed it, here's what they were. It's in chapter 9. There's 9. Here we go. The one that you had assigned, this is what somebody else set up the syllabus, but this got 3 ranges in it. That's really ugly. So I gave you back one that's only got 2 ranges.
Oh, okay.
Now the truth is, if you noticed it, this one you can solve using just 2 ranges. Due to this symmetry here, you know that's going to go back to 0 and that's going to go back to 0. You could just solve that half. But I didn't think most of you would notice that, and you'd sit there and work out 3 ranges and you'd have 18 pages of work. So
That's what I would have done.
go to that one.
Okay, thanks.
Okay.